Okay, I want to thank the workshop organizers for putting this together. So I have to apologize. This is work in progress. There's certainly no theorem in complexity theory, and there may or may not be a theorem in math by the end of the talk. But nonetheless, I think there's some ideas I'd like to present and a general context of how to use algebraic geometry to prove lower bounds. And I want to advertise this both to advertise the algebraic geometry and for computer scientists and to advertise the computer science for the algebraic geometers. So there's a lot of very interesting problems in complexity theory, but just to fix ideas, I'm just going to focus on the flagship problem of determinant versus permanent. So we have this determinant polynomial and this permanent polynomial. And for the moment, let's both be for n by n matrices. So these are a homogeneous polynomial of degree n on the space of n by n matrices. So maybe I'll write that as Sn of E tensor F. So this is also homogeneous polynomial on space of n by n matrices. So E and F are just Cn. And you can, if you like, and I like, to define this as the unique polynomial.
Well, it's Cn.
This is my talk. I can have it be polynomials on E tensor F star. Invariant under left and right multiplication by matrices with determinant 1. So I'll write that as SLE cross SLF. So SLN is the space of n by n matrices with determinant 1. And this is unique. Mathematicians use exclamation point for unique. So it is characterized by its symmetry group. And so complexity theorists tell us that determinant is best polynomial. And we all believe that as mathematicians. But here is a representation theoretic reason why it's a best polynomial. It is characterized by its symmetry group. And to mathematicians, so complexity theorists believe permanent is a beautiful polynomial. As a mathematician, it took me a long time to warm up to the permanent, but it does also have this beautiful property that you can simply define it as the unique, I'll write unique, I may even spell it correctly, polynomial up to scale. Well, of course, we already used up our favorite group of left and right multiplication by determinant 1 matrices, so I can't have the same conclusion. So let's think about other nice things we could do. Well, instead of arbitrary matrices with determinant 1, what about permutation matrices? And that's what this one is. And I'll write it like this. So this is permutation matrices acting on the left, and these are permutation matrices acting on the right. And it's the only polynomial. It is characterized by its symmetries. So in representation theory, we can agree that these are magnificent polynomials. Questions? Okay, now the flagship conjecture.
No, but the torus also.
No, you forgot the torus.
If I swap two rows of a matrix, its determinant changes.
The
The
torus keeps it invariant of determinant 1.
What?
The torus of determinant 1 keeps it invariant.
Permanent.
You need torus, I think.
Yeah, torus, you need torus.
It's also invariant under the torus, but it's already characterized by this group.
He's not giving us.
No, that's not true.
Oh, so I need the...
You need torus there.
You need torus.
Sorry.
Now it is all.
So these are the diagonal matrices, or if you like,
The normalizer of the
the normalizer of the tori.
That's what.
Yes.
When the determinant is invariant under that group, then its square will also be invariant under that group.
But here is
this
the
It's a unique polynomial in this vector space
Okay.
that is invariant under that group.
Right.
No, there are many polynomials in different spaces invariant under that group with different representations. We're talking about embedded. So the flagship conjecture of geometric complexity theory is that you cannot write the permanent. So here m is less than n is as a linear combination of determinants or even in the orbit closure when n is some polynomial m. So m is less than n in this talk. I apologize.
We should not go down too much because
Okay, I will not go down anymore. So it's known, okay, when n is less than m squared over 2. So at least it's known for a quadratic polynomial with some constant. And that result in mathematics, I think computer scientists are not aware that there's actually a slightly stronger result than that. Namely, the way one tries to prove this conjecture is to find a polynomial that vanishes on this set that does not vanish on this point, or a module of polynomials because we want to use our group actions. So I draw sort of a cartoon picture here to explain the result that implies this. So there were a module of polynomials, union green. So we found a module of polynomials on the space of all polynomials, on space of degree n on space of matrices. And the zero set of this module contained what we wanted, the green, and it also contained some garbage. And the full theorem is that not only does it contain the green plus garbage, but that the garbage stays away from the green near the determinant. That is, that there's a neighborhood, a Euclidean ball, about the determinant without any garbage in it. That is, another way to say it is that this is an irreducible component of the zero set of this module of equations. So it's stronger than just a bound here, but that's not the subject of today's lecture. But somehow complexity theorists...
garbage is exponential. Dimension of the garbage is exponential.
The dimension of the garbage is, yeah, it's exponential, but small exponential, whatever that means. All right, so let me write down what I said because it's so important. The method of attack is find GLN squared modules of polynomials vanishing on the determinant and not on the permanent. Okay, that's the plan. Okay, and what I'd like to talk about today are some promising approaches to this plan. So first, I'm going to review a method first used by Kayal and then used extensively in this 4-author paper. You heard a little bit about it last night, called the method of shifted partial derivatives. And then I'd like to explain 2 different generalizations. And I'm going to talk about it in the context of this particular problem, but you should think of those generalizations as being potentially useful for arbitrary circuit lower bound problems. Anytime you have a complexity class an algebraic complexity class that can be characterized by a polynomial that's characterized by its symmetry, these kind of methods are hopefully applicable. Right, so let's get started. So the good news is I got a new pen. The bad news is it doesn't want to erase it, so it marks it well. All right. So before I explain the method of shifted partial derivatives, I should go back in time a little bit to explain the method of partial derivatives. So if you're a mathematician, I have to go back in time. Well, if you're a computer scientist, I have to go back in time to the 1990s. It was pioneered in computer science by Nissan and Wigderson. But if you're a mathematician, you have to go back to the 1800s. It was pioneered by Sylvester, who gave it the funny name of catalecticants. And then later it picked up some other names as people rediscovered it, one of which is flattenings, which is the one I tend to use. I don't know why. I think that was Behrend who coined that one. So I'm going to have a vector space. And I'm going to have a homogeneous polynomial of degree n on the dual of the vector space. So just homogeneous polynomial of degree n in capital N squared variables. And we consider the following linear map. Let me call it pk n minus k. So this is, if you like, the space of homogeneous differential operators of order n minus k on this vector space. So a differential operator will map a polynomial here to a polynomial of degree k. And the image is all partials of order equal to k. All partials of p. So if you have a lower bound on the rank of this map, you have a lower bound on the complexity of your polynomial p. So we get polynomials on the space of polynomials. So the size r plus 1 minors of this linear map give polynomials on the space of polynomials. Okay. Degree r plus 1, because the entries of the matrix of this linear map are linear in the coefficients of the polynomial. So the total degree is r plus 1. Okay, so let's do some examples. If p is just x to the n,
What is R?
the rank of p, k, n minus k is equal to 1. R is the rank of this linear map. If p is a monomial, the rank is equal to n choose k. You get the most bang when you take k about n over 2. This is like 2 to the n over square root of n. When p is the determinant, we get n choose k squared, so 4 to the n, roughly. And then, so I should say the possible, I should say p generic, the rank is capital N plus k minus 1 choose k. So if in this space, when n is equal to n squared, then that number would be n squared plus k minus 1 choose k. And when p is the determinant, this number is quite a bit smaller than this number. The determinant is pathological. What is the image of the map? It's just the minors of size k, because you take derivative of a matrix, you have Laplace expansion of determinant. Any questions? Okay, so the first unfortunate piece of news for this technique is the permanent ties the determinant. And for the exact same reason, because you have Laplace expansion. And so we need to do a little more if we want to distinguish them at all. So let's take this map and try and beef it up a little bit. So let me draw it like this.
So can I ask, this Young flattening is equations for what?
I have not discussed Young flattening yet. Yes? That's part 3. We're on part 2. I promise you I will tell you part 3. Okay, so we have to beef this up. So what I'm going to do is just tensor this with the space of polynomials of degree t, and for the moment do nothing. And now there's a natural map. If I have a homogeneous polynomial of degree k and a homogeneous polynomial of degree t, I can multiply them to get a homogeneous polynomial of degree k plus t. And this is the shifted partial derivatives map. So in GKKS, this is denoted, I better tell you how it's denoted because it's this. I have an unfortunate, not only do I reverse n and m, I'm reversing k and n minus k. This is denoted d equals n minus k, p equals t. And I just want to bring to your attention that this is n minus k and not k here. It's just bad habits. I'm a little dyslexic. That's only for the experts, for Kayal. The rest of you don't worry about that. So you don't need this unless you want to connect with last night's talk. So let's go through our examples. I erased the first example. I just have to erase the answers. They change a little bit.
So how is this?
So P generic, yes?
How is this pk minus kt defined?
What?
Oh, you just.
I composed 2 linear maps. The one we've been discussing with the multiplication map. Okay, so P generic, you get the whole space. Oh, yeah, k less than or equal to n minus k. Even before I needed that to not be lying. Forgot to say that. So, I should tell you what this is as far as a geometer is concerned. Geometrically, you don't want me to write this far down. Okay. Geometrically, what am I doing? Geometrically, call the image of P n minus k, k the n minus kth Jacobian ideal of P, and let I, P, k denote the ideal it generates. Denote ideal it generates. Then the rank of this linear map is the Hilbert function of the ideal, not of the coordinate ring, of the ideal in degree k plus t. So I'm trying to be as bilingual as I can, but I don't properly speak computer science. And later in the talk, you'll see I also don't properly speak commutative algebra, so I may have to get corrected once in a while by the experts. But
IPK, where is this ideal being generated?
this ideal, So for every k and every t, I get a linear map. Okay? Now let's fix k and allow t to vary. What the images of these linear maps are exactly the component of the ideal in degree k plus t. And therefore, the rank of this linear map is nothing, as a function of t, is nothing other than the Hilbert function of that ideal generated in degree k. So if it's generic, it's surjective, so the rank is n plus k plus t minus 1, choose k plus t. If for this one, it's n plus k minus 1, choose k, because if I take an nth power and if I start with a kth power, this multiplication map is an injection. It has no kernel, and I'll return to that issue later. That actually will be kind of sadness for us. In this case, this sort of known to the experts, but we couldn't find it written down. The rank is this sum of binomial coefficients. And I'll say it now because I won't have time later. We actually have the full minimal free resolution, which is also sort of fairly standard if you know Stanley theory. So the determinant has an interesting story. There's a classical answer, which is not so useful, but I'll write it down. Well, it's useful for a particular k and a particular t, but if you're a computer scientist, as I've learned, you want to do asymptotics. And then this is a little hard to compute. So the ideal is known very explicitly. It starts out with the size k minors, and you pick up all polynomials in sim n of sim k plus t in E tensor f. You pick up, so this is splits as a direct sum of a whole bunch of s pi e's tensor s pi f's, where pi ranges over all partitions of k plus t. And the ones that are in the ideal are the ones where the number of rows of the partition, the number of skew symmetries, is k, because you started out with k by k minors. So you have to keep those skew symmetries. You can't get rid of them. So that's nice, but hard to work with. And then Sturmfels has a more effective way using Grosvenor bases to estimate. Well, he has an exact answer, and it is a good tool for estimation, unlike...
Now you're writing for the dead and permanent this dimension of pk, rank of pk minus kt. Is that what you're writing?
Yes, yes. Yes, I'm still on the determinant. I'm still on the determinant. And now let me tell you something that's worse than Sturmfels for just this particular question, but it will be more important later. Lascaux, and made more explicit by Wyman, is, I'm not even going to write it down, it's a description in terms of alternating sums of products of binomial coefficients. So already this is bad, that this is an alternating sum. This is a sum of products of binomial coefficients. And then you can make it even worse by making an alternating sum. But we'll see that that actually has more information in it later in the talk. And then for p equals the permanent, the rank, well, this is not known properly. If k equals 2, it can be deduced from work of Lombacher and Swanson around 2000. And for k equals 3, can be deduced from work of Kirchhoff in 2008. And more on this later. When I talk about minimal free resolutions, I'll give you a little bit more information about that. Now I have some bad news. For the computer scientists, this won't really be hard news because I think this was known qualitatively before, but the quantitative result is sad.
So one does not know an answer for the perm for arbitrary k.
That is correct. And part of this talk, the last part of this talk, will be progress towards that question. So here's the unhappy proposition. If m is less than n over 2, then, oh, I forgot. Yes, one more shifted partial. Oh, I'll write it up here. Yes, this is an important one. GKKS, if P is equal to sum of two monomials, the rank of this linear map is at least the sum j equals 0 to n minus k, n k minus j, k plus t minus 1, k plus j minus 1. Hope I got that right. Oh, no, that's the wrong one. That's the wrong one. That's the other. That's that one. Sorry. I thought that looked funny. There's no sum in theirs. That's why. Theirs is nice because there's no sum. It's 2n minus k, choose 2n minus 2k times n squared plus t minus 2n plus k, choose t.
This n squared, where did it come from?
What? N squared is the number of variables.
N is the number. In this polynomial, n is the number.
Yes, but I'm considering this inside sim n of cn squared, and it just happens to use only 2n of the variables. Thank you.
Y1, Yn are separate from x1, x2?
That's correct.
So N squared is capital N or no?
N squared is capital N. So I'm considering this, just like we do for the permanent, as a polynomial in a bigger space that only happens to use a few of the variables. Few-nomial, I think you guys call it.
No.
Something like that. Okay, well, whatever you call it. Okay, but anyway. Few monomials, thank you. See, I told you I need corrections for both languages. Yes?
Paper GKKS, they calculated this for determinant, but...
No, they calculated it for this, and they stated it for determinant, but the proof, they used that polynomial. So this is in their proof, if not in their statement.
But it's funny that they have no sum, but for a single one, there is sum.
Well, that's because this is an estimate and this is an exact answer. That's asymptotics.
Sorry, that's an estimate.
That's asymptotics, but it's a sharp estimate in the sense that it's true for every n, k, and t within the admissible range. But it's just an estimate. It's not exact.
I missed that.
Yeah, that's why it's greater than or equal to. Right, but unfortunately using that result, if m is less than n over 2, and remember we want it to be at least smaller than square root of n to say something new, then shifted partial derivatives cannot show that L to the n minus mp is not contained in the gln squared orbit closure of that polynomial for all p with the rank that looks like the permanent.
You mean n squared by 2 or n by 2?
N by 2. That's why the frown. If it was n squared over 2, I'd be delighted because the rest of this talk is going to be about going beyond shifted partial derivatives, and if shifted partial derivatives could equal the old world record, we'd be throwing a party. I mean, that'd be awesome. But unfortunately, that's not the case. So let me finish this statement. For all p with rank this, and in particular, the permanent perm And see, this thing sits inside. This is a degeneration of the determinant. So the same thing is true for the orbit closure of the determinant. Right. So that's bad news. Sorry to be bearer of bad. I didn't want to erase that. Let me.
So what's it say? Because the determinant has that same rank.
What? Yeah, but we want to separate permanent from determinant. And this says we cannot do it by this method
Okay, yeah, that's.
within that range. But I agree, the method also, the same proposition could be used to prove that you cannot separate the padded determinant from the padded, but we don't, that's not our problem. We got enough problems in our life. We don't need to add to them. So let me keep this on the board. Eraser happy. All right. So the
ELS result. This proposition is ELS result.
yes, yes. So 2015 paper, and it may even become ELSW, but that's for the last part of the talk. Right. So we want to go further. So let me tell you a parallel world.
So these equations, whatever these equations are shifted partial derivatives,
What's the question?
did you calculate the dimension of the garbage on the boundary that
Well, this proposition is game over for shifted partial derivatives. Okay, so we don't need to worry about them anymore. But we can use them as a starting point, just as the method of partial derivatives was used as a starting point for shifted partials, and you can get a lot more out of shifted partials than partials. If we use this as our starting point, maybe we can go further. Yeah.
Probably good to say that in general, these particular complexity measures have some intuition, but that any linear map may serve us well. It may come from.
That's what I'm about to say.
All right. Sorry.
Yeah, you guys are way ahead of me, and yeah. So that's
in the case you are not going to say this.
dígame.
The advantage of using a linear map in the context of algebraic circuit lower bounds is that, of course, these measures are sub-additive.
It's sub-additive, I agree.
You have to say, and
Yes.
all of them will be like that.
That's correct.
In some cases, like the shifted like the partials, and in some sense, the shifted partials are also closed under multiplication.
Yes.
And for that reason, they serve as a natural complexity measure for arithmetic circuits. That's what you're doing, multiplying and adding. So we can invent things very different than this. And the question, what's the limit of any linear maps?
Yes. That is what I was planning to say. But thank you. You said it better than I could.
Which linear map are talking about? Where?
Well, here is he showed you two, the partial derivatives and the shifted partials. Now he has a new suggestion.
Oh, okay,
Yeah.
okay. I see.
Yeah. So let me actually. Yeah. So, Ottaviani and I were studying Waring rank of polynomials, or Waring border rank of polynomials, and we introduced a method that generalized existing techniques at the time, that is to say flattenings or catalecticants. And the idea, I'll give you a very explicit example in a moment. So you embed your space of polynomials. So again, when we're looking for modules of equations, we're looking for GLV modules. And those are given by at least the polynomial ones. I'll write as S pi v, where pi is a partition. So what this should be is we need to embed our space of polynomials inside the space of linear maps from some module to another. This will work where pi tilde is formed from pi by adding n boxes, no 2, in the same column. This is the Peary rule that tells you that this is sort of all the possible things. So let's, given a polynomial, let's let p pi tilde be the resulting linear map. Oh, dual there. Right. And again, the rank of this linear map is a measure of the complexity of the polynomial p. So let's do just the first example, partial derivatives. So your first, so v will be Cn, capital N. So for partial derivatives, you start off with a diagram that looks like this, which is n minus 1 by n minus k box. That's pi. And then I'll do pi tilde. I got to add some boxes to that. So I need to add n boxes. So this is n minus k. So I add the n boxes here. And this module, as far as polynomials are concerned, this is all trivial for the special linear group. So this thing I might as well consider like this, which is sim k of v.
N is precisely the dimension of B or what?
B is any vector space sufficiently large dimension that I don't get 0.
N is not the dimension of B.
Big N is dimensional.
Capital N is dimension. So I have to pick my pi based on n. And if I do shifted partials, let me just use the same picture. For shifted partials, the picture is exactly the same, except I start out a little further, and so then here I get sk plus t. So I still add on n boxes, but so shifted also falls into this framework. But we were thinking about wearing rank.
It's not so little. The T is much bigger than...
To prove a theorem. But you can define it for any value of t. I'm just talking about where, and also to prove a theorem about something you care about, you want to have t that size. But to prove a theorem that mathematicians care about, you may not want to have t that size. Okay, this is, I mean, I understand that mathematics only exists to serve computer science, but sometimes we entertain ourselves with our own little questions that, you know, even if no one else cares, we like them. So,
what does one do who is both a mathematician and a computer scientist, I wonder?
Look, let's talk about this. Let me finish this lecture. I'm going to try and break tradition and not run over by 10 minutes. But I doubt, I don't know, depends on how many questions. But more questions, the better, and we'll just live with it. So remember when I talked about this Hilbert function, or this Hilbert flattening, I'm going to call it now, it was absolutely useless for wearing rank, because when you're looking at an nth power, this map is injective. So we would never think about that if we're studying wearing rank. But if you want to get the most juice, you go to the other extreme. And we looked at this map, sim n minus k v star tensor lambda qv. So first we did the same thing. To sim kv tensor lambda qv. Nothing happens. And then we take, well, I was born in mathematics as a differential geometer, so I think of this as exterior derivative, or a Kazul map, if you want, to sim k minus 1v tensor lambda q plus 1v. So let's call this p k n minus k wedge q. So where d of some polynomial q tensor y1 wedge yq is just the summation over the partial derivatives. I'm going to be a little sloppy now, but you'll get the yq. Okay, so here pi tilde after you prune, so this map should be pruned because there's stuff that's mandatory kernel, and the good part of that map comes from the partition K1 to the Q. And this is roughly, as far as wearing rank is concerned, 2 times better than partial derivatives. So it was possible to prove some new things about wearing rank. Well, so you remember those lower bounds? So we're comparing, in wearing rank, we're comparing how many, we want to write a polynomial p as a sum of nth powers, and we want to get a lower bound for that number of nth powers that we need. Using flattenings or partial derivative method, we got a bound, basically the rank of that flattening map. And basically here you can potentially get about twice as good of a bound. Okay? And you do get about twice as good of a bound. So as far as computer science is concerned, that's not, so serious yet, but let's continue nonetheless. And so now, though, the new game plan.
So this D isn't exactly the Durham differential. If
Yes, exactly. Exactly. That's why I called it exterior derivative.
And here, even though SKV tensor STV, should it be thought of as differential operators with polynomial coefficients?
You may, if you like, but well, actually here, you want a differential operator with polynomial coefficients. This is the differential operator with polynomial coefficients.
That's what I
Yeah, good. Good. So now the goal becomes, the short-term goal is find pi and pi tilde such that determinant pi tilde has low rank. Right? If this linear map has low rank, then you can hopefully prove that something is more generic than the determinant. But yeah. So, right. So my student Cameron Farnsworth has been working on this, and so I like to call this one the Kazul flattening. And he showed that this Kazul flattening, in fact, the determinant is more generic. So, as a mathematical result, this is very interesting, but
More generic than what?
so you get a better lower bound on the border rank of the determinant from a Kazul flattening than you get from a usual flattening. So that in itself is not a disaster, but at the same time he proved that the permanent is also more generic, but of the same order of magnitude, and it's sometimes even worse. Since I'll just take 2 seconds to mention a crazy conjecture by a crazy guy, Gervitz, who actually conjectures that the wearing rank of the determinant should be actually lower than the wearing rank of the permanent, and somehow that explains why the determinant is easy to compute and the permanent hard. So this is evidence for Gervitz's conjecture, and he's a serious guy, even though, yeah, that conjecture sounds strange, but it is actually not unreasonable. But I don't have time for that. So that one's no good. So I should mention a recent very exciting result by Luke Oding and Han. Sorry, I shouldn't. Han and Oding, which used the staircase. And then they showed a new lower bound on the rank of this x1 ... xn. Remember, the old was 2 to the n over square root of n, and they got the sharp result, which is 1/2 2 to the n, otherwise known as 2 to the n minus 1, but they got rid of the square root of n.
It doesn't depend upon Q.
There is no Q here. They used the staircase. They did not use, this is pi staircase.
What is the staircase?
The staircase partition,
So what is this? A minus 1, A minus 2, and so on.
Right.
Okay, exactly.
yeah. I can't draw it so well. And then Farnsworth tried the staircase, and you got the same thing, same phenomena as with the Kazul for the determinant. So I should say, though, that the determinant just on, that's coming in the last part of the talk, that for this Hilbert map, though, the determinant is less generic than the permanent, just not as much as we want. And I also want to say that this indicates that we're going to need, there's some limit of this method, and there's only 2 examples I know of geometrically defined equations that do not fit into this method. One was the one that this lecture started with, but those are still determinantal equations, just the entries in the determinant are not linear forms, but polynomials in the coefficients. But there's these equations due to Brill for exactly the orbit closure of this x1 up to xn that are geometrically defined and go beyond this. So the linearity is good for all the reasons Avi said, which is what I was going to say now, but it's bad that it seems to have an inherent limit. And we have some examples in geometry that go beyond that. So one is Brill's equations. And Yanghui Guan is doing some interesting work generalizing Brill's equations in a way, because of their nonlinearity, you can't just use them subadditively, but he's working on a variation that will enable that. So exactly addresses the 2 questions you posed. Yeah, go ahead, Avi.
Just a comment. If you just want to get actually not half 2 to the n, but 2 to the n for the monomial, you can get it much more simply. You restricted yourself to partial derivatives of
I know.
a fixed order. If you
Yeah.
take all orders, you get 2 to the n. So
Yeah. But that's for, anyway, yeah. Let's,
These Brill's equations that you talked about are for the Chow variety?
what? This is, Brill's equations are for the Chow variety. They are not of this form, but they are determinantal. And I think those are in my personal opinion, sort of Brill's equations are the best path to sort of breaking this inherent limit of the linearity. But that's a personal opinion. I guess everything's a personal opinion. All right, so.
Just for clarification, this Farnsworth result is for this pi.
So there's Farnsworth results 2 different partitions. One is the hook that Ottavi and I were using, and one is the staircase. In both cases, they each give lower bounds on the Waring border rank of the determinant. And unfortunately, the determinant is like supercharged for those in that its rank does not drop by much for the extra map. So it's for the permanent versus determinant, it's not so good. But
You are using this model. This.
well, the model of this model, I would say, is a better picture.
Replacing SKV.
So he did 2 things. He replaced this SK by lambda K, but then there's something more complicated, inspired by the Hahn-Oeding result, replacing it by a staircase. So there's 2 results. Okay? Right. So the Hilbert function, one way you can compute it is as the Euler characteristic of a minimal free resolution of an ideal. And so you get much more information if you do that. So I'm going to write it sort of representation theoretically, since I'm almost out of time. Well, since I am technically out of time, I'm just going to start saying things instead of writing them. So Jerzy Weyman's talk told us that if you can compute a minimal free resolution, you can get a lot of good information. So this is the so now we have this ideal I that I was talking about. In our case, it's the ideal generated by partial derivatives. And these are the generators.
So you are resolving S mod I.
No, well, it's the same thing, right? Okay. I mean, I could.
So you are resolving sim V by I.
Yeah. Okay. So here, these are the first relations among the generators. A basis, a module of relations, and the larger this is, means our ideal is more pathological. That's not quite true. That's only if you fix the size of the generators, and then the more relations you have, the more pathological. So a quick example, V is E tensor F, then M1.
More pathological?
So we're looking for ways of proving a polynomial is pathological. So if we we take partial derivatives, we get an ideal. If we fix the dimension of the space of partial derivatives, then we want something that's more subtle than that, right? So once you fix that size, the next measure of pathology is the size of this vector space, which is the relations. So if we're starting with the determinant, so I is the size generated by size k minors, then the Laplace expansions give us linear relations. If I take a k plus 1 by k submatrix, and then I repeat a row to make it k. So I repeat this last row. I have a k plus 1 by k plus 1 submatrix whose determinant is 0. I form like a tensor Laplace expansion where I put the linear form here and the size k minors in the expansion here. When I map it over here, I get 0 because I erase the tensor product. And so that's the kind of thing. And so we have a lot of linear relations here for the determinant. Since I'm out of time, it's too bad. I wanted to talk about, so first of all, Lascaux computed this completely, and Weyman made it even very explicit in his book. He views it as just an exercise, but I read Lascaux's paper, and it's a challenging exercise. It's very explicit in terms of modules. It's for the size k minors, and so it's basically these things are generated by hooks of various sizes where the hook is long, and the unique proposition, which I'm only going to state vaguely since time has been up, is that for the permanent, the subpermanents, size k, these MJs, so these are the MJs all look like this. The MJs contain hooks, but now I have to tell you what these hooks are. We no longer have the special linear group. We have the permutation group. So these are hooks now are modules for the permutation group. And the hooks you get here, which are modules for the permutation group, are the transposes of the hooks you get here in the linear strand. So it contains those, and we conjecture that, in fact, that's exactly the linear strand. And Jiří has some ideas how to prove that conjecture. And the point is now that we can exactly compute, at least not too far into the minimal free resolution, we have exact formulas for this Hilbert function of the ideal generated by the subpermanents up until a certain point, and that's why it's work in progress. We hope someday to get the whole resolution about the permanent. That will give us a lot more information about the permanent, and then we could, because the permanent is not a generic polynomial, but we need to know that in some kind of coordinate-free way to have invariance that will enable us to separate determinant from permanent. Thank you for your time.
So this accounts a little bit for these differences of binomial coefficients. This accounts for the altering sum of binomial.
Yeah, that's exactly. Yeah, it's every step along the way. Yeah.
Is orbit closure of the determinant saturated?
Sorry, plus fort.
The question is about the orbit closure of the determinant.
Yes.
Is it saturated in the GIT constant? Is it a fiber of the GIT constant? Because you are looking for GLN square invariance. All the minors, all the rank, all these linear maps are GLN square invariance by construction.
Well, they're modules. They're modules. They're not invariants. Yes.
For example, here,
So anything in the GLN squared.
the rank is invariant, not the minor.
Yeah, the space is.
Space is not invariant.
No. So that's what we want to extract numerical information from this geometric picture. Yeah.
So this method, including your exterior thing, how much do you think you can push? Can you go beyond a square, or it's unclear where you can go?
No, I doubt. Okay, so maybe, just maybe, we could sort of tie the world record, maybe even a little bit beyond that, but it's going to be game over soon after that. But this is not the end of the story. This is not, this is, I think, the end of the story for determinants of matrices who have linear entries in the polynomials. And one's going to have to deal with, I think one can still stay in the context of determinantal ideals, but you have to go to matrices where the entries are no longer linear. That's going to make life much worse. For the reasons Avi explained, but I don't think we have a choice if we want a geometric construction of these modules.
I want to say here is like, in some perspective, our reason was not just to study determinant versus permanent. The real reason was to able to understand like different complexity classes, and even determinant is not the unique polynomial which is complete for class P. So there are many other polynomials, and if you write down them, they have different geometry. It's very interesting to study with different polynomials, but like determinant is a good starting point to do these calculations because it's kind of relatively easy and relatively long.
That's only computer scientists can have that optimism. Frank.
What's the dimension of the variety of different expressions of the permanent?
I told you. That's open. That's open. We only know it in the extreme cases, and even then. So we know it for like k equals 2 and 3. And n-1, everyone in the world believes that it's codimension n, but I've not seen anyone write down a proof of it.
One of the things, I mean, your map of the partial derivative map is very differential in the Kosovo complex.
Yes.
But if you look at the higher graded components of the higher differential of the Kosovo complex.
Right. One of the things on our table, which I did not have time to mention, is one way to merge these two techniques is to tensor this thing with the Kosovo complex, and then look at that resolution.
Because there are theorems
Yes.
like the top Kosovo homology group.
Yes. That's on the plate, but the plate is already very full, as you know. We want to first kind of do as much as we can with the so-called easy case before we move on to the even more ridiculously hard case. Matish.
When we construct these equations, we get equations of certain secant varieties. And
Yes.
First, we checked with the error. Those that we checked always vanished on linear spans of arbitrary schemes of the same bounded length.
Okay.
My question is it expected or no, not to be true that these equations always vanish on the appropriate factor?
We'll have to discuss that offline. And that's another way of saying I don't know.
I want to throw a completely, there is a lot of information that we know. Permanent has been studied for various other.
Permanent has been studied substantially, but its algebraic geometry is extremely poorly understood.
I just wonder, so, there was Van der Waals conjecture, a big achievement, and we now have two separate proofs for this. There is Bergman's upper bound. The two things have nothing to do with each other. I find it a little hard to believe. No, I mean, not that I can offer a way of making contact between. I find hard to believe that.
Well, so already it's been, there's tons and tons of literature on the determinant even going back, right? And to convert that to information you can use in this setting is not, I mean, there's been some effort expended on that already for the determinant. And when you get to the permanent, you're in combinatorics. And if you want to win this game, you have to avoid combinatorics because that'll just, I mean, well, explicit combinatorics. You can only do asymptotic combinatorics. I should say it that way. And that, like here, when you study representations of permutation group, you have to understand the asymptotics of those representations, not, we like Shraw was talking yesterday, we were just trying to find out if one stupid-looking module is in the ideal of the orbit closure of the determinant, this basically the simplest thing you can describe. We can't even do that, and when we tried, we got face up to alone Tarsi and all these other horrible conjectures, or beautiful conjectures that no one knows how to solve. So one has to kind of try and avoid that somehow.
Okay. Yeah. Thank you.
No?